Remember me high. What I should do, should give a lecture like that one day. Wouldn't that be cute? All right, so here we go. This is heat of fusion. This is heat of vaporization for water. These are just two terms that we're going to be using in just a moment. Okay. Now, what I want to do is this is energy, all right, on the y-axis, and this is temperature on the y-axis and energy on the x-axis, all right? Now, what I want to do is I want to know how much energy is required. So we're looking for energy to raise the temperature, okay, of 13 grams of ice, okay, at -5 degrees centigrade up to 103 degrees centigrade. So here's the problem and here's the graph. I have myself a block of ice that weighs exactly 13 grams. And I want to know how much energy is going to be required to raise the temperature from -5 degrees centigrade up to 103 degrees centigrade. All right. So the first thing,
I'm trying to fix my air conditioning.
oh no, I know what you mean, right? It can get all out of control. The first thing we got to do is we got to have the heat up ice, which is a solid, okay, from -5 degrees centigrade up into 0 degrees centigrade. Now that's going to be a solid as well. And when you look at this graph here, you are going from this point here at -5 degrees centigrade up to that inflection point at 0 degrees centigrade. You see, to add up this total amount of energy, we're going to have to find ourselves around this curve. In other words, we just can't say, well, what's this number minus that number? Okay? Well, because we don't know what these numbers are. Is the reason we can't say that. Okay? But we know what the temperature is. So what's the equation for that? The heat equals the mass of the ice times the specific heat of ice times the final temperature of the ice minus the initial temperature of the ice. Now, what's the thing I need? I need the specific heat of the ice. Now, the specific heat of ice is not given there, so I'll have to look that up for you just really quick. So do your guys' boyfriends not carry your purses for you? Me and Bonnie Singer. That's the way you want it, right? All right, 0.5. That's awful. Get out of my way. Okay. 0.5 calories per gram degree centigrade. This is the specific heat of ice. Now, I want to work in joules just because that's the way I like to work, because it's an SI unit, and 1 calorie is the same thing as 4.184 joules, right? We're going back to chapter 2, still on the conversion. 0.5 to somebody else's purse. 4.184. That's going to be 2.092 joules per gram degree centigrade. Okay, so this right here would be a constant that I give you on the exam. Okay, so what's the mass? 13 grams. And the specific heat is 2.092. The final temperature of the ice is 0 minus the initial temperature of the ice is -5. So how much energy in step 1 do we deal with? 13 times 2.092 times 5. So that would be 135.98 joules of energy to go between these two black dots. Okay, so what are we doing? We're trying to find exactly how much energy it would take to heat up a block of ice that started at -5 degrees centigrade and go up to 103 degrees centigrade. Now, do you see how you've got this flat region here, this plateau? What's the temperature at this black dot where I'm pointing? 0. What's the temperature here? So this is what is called an isothermal. That means it's the same temperature. Now, does it take energy to cross that barrier? Yeah, look at how much energy that's going to take. It takes quite an amount of energy to cross that barrier. And that's what's called a heat of fusion, right? Like if you fuse bone together, what are you trying to do? Make things stick. Well, the same way here with fusion, it's talking about freezing. To make things stick. All right? So, look on that page there and tell me the heat of fusion of water.
345.
How much?
335.
335 joules per gram. Okay. Now how much water do we have? 13 grams. So we're done. So what's 335 times 13? 4355. All right, so this is 4355 joules. So does it take a lot amount of energy? Yeah, take a look at that. Going from this point to this point takes 4,000 joules of energy. And what are you doing? You have simply went from ice, which is a solid at 0 degrees centigrade, to liquid at 0 degrees centigrade. It's isothermal. We have not changed the temperature. So see, whenever you freeze ice, they have these solid forces, these crystal packing forces. There's all sorts of forces that happen inside of solids. And to break those apart takes a huge amount of energy. All right? And that's the energy that we did there, is breaking apart the forces that hold ice together. 4,000 joules. All right. Now what's the next step? Well, we're going up the curve, inflection point to inflection point. So we're going here from here to where? There. All right. So that is step number 3. Now, step number 3 is as follows. We're going to take our liquid water, which happens to be at 0 degrees centigrade. Okay? And we're going to heat that up to liquid water at what temperature? 100 degrees centigrade. So we're going to do a full 100 degrees centigrade change. All right, Q equals MC delta T. Okay, what's the mass of water? 13, right? Because the mass doesn't change. What's the specific heat of water from your table? You got that, Sandy? What do we got? 4.184? We got it? Yes, no, maybe. Okay, who's not located the table? Then why are you looking at me like trout? What's going on? Are you texting in my class?
No.
Good.
I'm reading.
You see it there? 4 point. Okay, it's not in the chart. Well, that's the specific heat of water, right? You remember from chapter 4? Specific heat of water is 4.184. Okay, what's the final temperature of water? 100. What's the initial temperature? 0. So how much energy then does it take to traverse that whole entire temperature range? Well, 13 times 4.184 times 100. 5439 joules. So that's step 3. Do you see how it takes almost the same amount of energy to just simply go from solid to liquid and change no temperature than it does to completely traverse a 100 degree temperature change?